Hi, my name is Sangkee. I'm kind of new professor I started from the last year, and this is just first year that I've been here in mechanical engineering. Before that, I was working for industry, right here, industry machine tool company, and then national labs and some venture company. And over the years, I kind of started developing some concept called manufacturing for design. So that's what I'm going to introduce today. I'm going to skip kind of short introduction here. You see, yesterday Apple announced the new iPhone 7, and this is the series of the iPhone that you've been seeing. And then this is the GE, the refrigerator, several different configurations, French door, and then SBS, and all those kind of the different type of the door configurations. What you can see is, probably you can see the design is pretty much consistent. Right? If you look at the Ford cars, then it's Ford car. You see the Chevy, then you see the Chevy, and the Camry is the Camry, right? Design is pretty much consistent. Do you see it as a brand image, or can it be a manufacturing constraints? What I mean by manufacturing constraints is that's what I'm going to talk about today. So in big manufacturing company, they practice design for manufacturing. How many of you have heard about the design for manufacturing? So you know that, right? It's basically, traditionally, designer come up with the design and send it to manufacturing. And the manufacturing reviewed, and there are a lot of stuff are not manufacturable or expensive, or it's just too much effort, right? So they send it back, design to the designer, and they have to modify, and they iterate this kind of cycle several times. And DFM is trying to shorten this cycle so that designers learn from the beginning that what's the manufacturing constraint you have, and what are the kind of the cost related to that specific design. So they learn about this one, and then from the beginning of the design, they accommodate all the designs, right? So that readily manufacturable. That's the basic concept of the design for manufacturing. Let's go back to the design here. So the experienced design engineer come up with a design which doesn't have to be iterate from manufacturing design to manufacturing kind of cycle, which means that over the years you kind of start to learn about your manufacturing capability in your company or your suppliers. And what are you going to do is that you just start to cut off all the features you cannot actually design, or some of the materials you cannot manufacture easily, then you start to cut it off. Then experienced designer start to put a lot of boundaries by themselves. And you are no longer creative enough to come up with a completely different designs. That's what happened. Actually, Kia Motor Company, one of the automotive industry company, their design was really bad. But then they hired a new person from the Volkswagen, and they come up with a new series of the K series, which completely can change the design. That's what happens. The companies, the designers in the company usually stick to their own design because of they are pretty much bounded by their manufacturing capability, right? So I see it can be a brand image. At the same time, it has a lot of the manufacturing constraint reflected in the design. So what if we give them a complete freedom to design without considering the manufacturing constraint? So that's what I am trying to pursue in my research here. So, I mean, one of the things that you recently recognize is that there are a lot of new materials kind of popping up. And how do you handle this one? Can we use this material for your design or products, right? So one of the categories is the emerging new materials, which is there are three categories of the emerging materials. Crisscross materials. What I mean by crisscross material is that this material exists and used in industry for a long period of time, but the certain industry doesn't use this kind of material. For example, automotive industry uses like metals, aluminums, and steels and all kind of stuff. Computer industry, plastics and PCB board and stuff like that. So there are certain set of the material being used in certain industry, but then now, computer industry started using aluminum pieces for their computer casing, which you never thought of as like an engineering material for their practices, right? That's called the crisscrossing material, as an emerging material. And the other one is the transforming non-engineering materials to engineering material, which means that the certain material exists already, but it was too expensive, or is too rare, or is difficult to fabricate. These three requirements doesn't meet, and it was not an engineering material. Now it becomes engineering materials. those things, one of the examples is going to be sapphire. Sapphire becomes cheaper and abundant because artificial synthesification can be used to generate the sapphire. The problem is getting cheaper too, but the problem is that manufacturing technology is not ready to fabricate this sapphire. So this is another category. And then there's completely newly synthesized materials. And the biggest challenge of these materials is going to be the mass manufacturable technology. Can we produce the quantity? So these are the kind of the manufacturing requirements. And the company is now trying to explore all these type of the materials for their future product development. Then, once we utilize this kind of materials, what's going to be the next? That's why I kind of start to come up with a new paradigm. So I'll skip this one, but the new paradigm I was kind of thinking about is the manufacturing for design. So the reverse concept, I think companies still practice the design for manufacturing for efficiency and productivity and everything, but as a research institute, we can actually solve this problem by applying this manufacturing for design concept. What it is basically try to remove all constraints and limits, manufacturing constraints and limits, and then see what kind of design we can come up. And then if we come up with certain new designs, and then what are the actual manufacturing challenges, that goes back to the DFM. And then we are trying to solve or trying to find an existing solution to those kind of manufacturing challenges so that we can actually come up with a new design and then new production technologies. This will give you a lot of opportunity. Innovative and creative product development potentials, and then innovative processing technology potentials, and there's a lot of business development opportunity too. I have one case study. This is the sample holder at the National Center for Electron Microscopy. It was not industry application, but when I was working for Lawrence Berkeley National Laboratory, this was a very interesting project. This is the sample holder NSAM, and as you can see, the shape of is like this kind of pyramid shape. And then on top of here, they put the material sample to get the image out of it. The problem was that, the reason they come up with this kind of design was that the manufacturing they have or their suppliers only can do this angle much. So that was the manufacturing constraint they have. The problem of this design is that when they shoot from the electron beam from the top, a lot of things are kind of reflected back to the image, creates a lot of noises. So I approached them and then asked them, what if you don't have, what is going to be your dream design for this sample holder? And please come up with your dream design, I'll see what I can do. So this was the current design, and then they changed the design to this shape. As you can see, it doesn't look much different, but it makes a huge difference. You can see this is the kind of the angle here. Now it is almost like a zero angle because you are kind of pointing toward the top. And with their current manufacturing technology, they were not able to fabricate this kind of shape to the accuracy. But my expertise in ultra precision machining, so that I was able to actually cut this part and then deliver to this part to them. And it increased the image resolution 1 order of magnitude higher. So it's a huge breakthrough. And then what they told me is when they discussed with their manufacturing engineer, the typical attitude of manufacturing engineers is that no, no, no. It's always like, this is not possible, this is impossible, this is too expensive, this takes too long time. But this was the first time they ever kind of encountered that, come up with a dream design and then try to solve the problem. So this is the kind of the attitude that I'm trying to implement in the manufacturing for design paradigm. Other than that, actually, these are my research topics. So as I just introduced, the manufacturing for design is the kind of the big category that I'm trying to do. Under that, my expertise in ultra precision machining is process physics. Let me kind of introduce what it is briefly. You know the CNC machining, the basically metal cutting process, but it's not only metal cutting process. You can cut many types of the materials, but there are several materials which is difficult to cut. But anyway, the conventional machining is, probably you are familiar with it, but when you say the ultra precision machining, this is the typical definition that surface quality you get is tens of nanometer surface quality. Actually now it goes down to the angstrom surface quality by machining without polishing anything. Just one cut machining can achieve like a several angstrom level of surface quality. And form accuracy is hundreds nanometer. That's like a large envelope we are talking about, so it's going to be much smaller. Same as the conventional machining, it has like all kind of milling, drilling, shaping, all kind of stuff. So basically, it's very exactly the same thing, but the precision that we are doing is going to be much higher. So these are the samples that I cut, previous company. So this is the micro needle array with 5 micron tip and then 200 microns length. It's a high aspect ratio micro needle. That was to inject it, for the injection for the child or diabetes, so that you can feel any pains. So that was very interesting project. This is the mirror surface. He talked about the mirror surface to have a lot of the optical quality, pyramid array, diffraction gratings, and all kind of stuff. And actually, so this Sunday, I am bringing this machine from Japan, the first time in USA. This is the 5-axis ultra precision nano machine, which means that it has a 3 axis of linear axis, and then 2 rotary axis. So each linear axis moves 1 nanometer, and then rotary axis moves 1 microdegree. Basically, you can create all kind of features with precisions. Talking about the semiconductor manufacturing process level. So I'm going to have this machine in my lab. And this is the kind of typical process we can achieve through this machine. So as I said, like scribing, milling, and turning, and then nano checker, and then we have a shuttle unit to synchronize kind of faster servo motion so that we can create a very subtle kind of features. And then the other aspect is the sustainable smart manufacturing. Probably you heard about nowadays smart manufacturing, but I've been working on the energy monitoring of the machine tool. Machine tool industry uses a lot of the energy, so trying to characterize how machine tool is using the energies, and then trying to come up with like a process level, operation level, and then corporate level, how we can balance the energy or reduce the energy consumption in the company. And this it will be through the IIoT, basically Industrial Internet of Things. So we are going to connect all these machines, sensors, and trying to monitor process from the corporate level so that we can actually balance the energy consumption and things like that. So this is the last topic that I'm going to work on that. So I'm looking for partners. You know, the manufacturing for design requires a lot of different manufacturing expertise. So some of the features, I mean, you have to do the laser processing. Some of the features you have to do the forming or casting, all kind of stuff. So I'm building my lab name is the Manufacturing Innovation Network. Actually, I'm building an innovation network of people which has each expertise in a different type of the manufacturing processes. And we are trying to do the MFD concept case study. Actually, now we are seriously discuss with the Samsung to go through this kind of MFT discipline in their cell phone development. And then we are trying to looking for the partner who are willing to adapt to this ultra precision machining technology or want to learn about this ultra precision machining technology. I think it has a lot of potential. And as I mentioned, that this NSEM sample holder was the one case study. If we kind of deliver some of this kind of capability to your company, and what kind of the product design, what kind of innovation you can deliver to your product design. So that's my question to you, so that probably you can utilize this technology to prototype your work and change your product design. And last one is the machine energy monitoring and savings through smart manufacturing. With that, I'm sorry, I was kind of rushing through it because I have a media interview right after that. So if you have any questions, this is the time to open up the questions. Thank you.
Okay. Question, can you kind of explain what the current comparable technology is for patterning, making designs that your technique is not constrained to?
I don't.
So if you want to make small patterns, maybe lithography might be a good way to make patterns.
Right. So now this ultra precision machining, his question is what kind of the pattern limit we can reach that photolithography and the semiconductor manufacturing can do in this manufacturing technologies. Basically, yes, we are reaching that level actually. Some of the features we can create like few microns to tens of nanometers. And in terms of the feature size, we go down to the tens of nanometers. But in terms of the surface quality, actually it beats now the semiconductor industry, the angstrom level. And the machine, next generation of the machine, we are going to probably, you will see in next year is going to be the angstrom machine, which is the machine linear axis. This huge metal chunk will move 1 angstrom command resolutions. So basically, theoretically, everything is possible. Right.